Good afternoon, good evening, everyone. My name is Abhin Dayal. I'm a PhD scholar and also PMRF scholar at IIT Hyderabad. And I'll be conducting this live session for week 11. I'll just share my screen and we can get started. I hope I'm audible and my screen is visible. Maybe if you can just confirm once in the chat or thank you. So, week 11, basically, in the course, the professor talked about how to improve GAN models, and also he talked about different types of GAN models that are available, which do different applications like in painting or domain translation or other types of super resolution and etc. So, and in the previous week, week 10, we talked about what are GANs exactly and what are VAs and like how do GANs learn the probability distribution of the underlying data, and how does GAN train using the adversarial methodology min-max optimization. And then we learned a little bit about the VAEs also, how they also learn the underlying distribution, but they learn a more explicit distribution, whereas GANs learn a more implicit. And because it's a more implicit learning, GANs are able to learn a more continuous or a smooth manifold, that is the latent space. And the generated data will also be fast and also better than the VAEs, which than the images generated by VAEs. So just in continuation to that, we first talk about the variants of GANs, and the first variant we talked about was the stack GAN. So as you can see, the main ideology behind stack GAN is, let's suppose you have an input of a text description. So if you can always take like an example, like if I give a text input like draw a flower which has a certain petal colors or which has a certain length, or like nowadays ChatGPT, not ChatGPT, like a DALI kind of a model. It takes inputs like draw me a painting, if Shakespeare, like some famous painter thought of a certain particular image, things like these basically. So the text description can be any such input where you are describing an image, what type of an image you want it to generate. So this input will first go into something called as a stack GAN. Stack GAN is this entire middle module. Now, stack GAN in itself has two stages. Stage 1 GAN, which you can see on the left side, and then there is something called a stage 2 GAN. So, what this does is basically it takes the text description, and then it also takes the latent space, which is usually a Gaussian distribution. It takes these two input to stage 1. It generates a 64 cross 64 image. This is, you can call it like a primitive sketch of what that particular text is. And this 64 cross 64 is then, we upscale, we make a better resolution, we send it as an input to stage 2 along with the text description, and then we make it a more realistic or a more uh, highly resoluted image, which is the 256 cross 256. So very simple process methodology. You just send the input of text along with that latent variable z, and then you upsample using the normal GAN methodology. Then you generate a 64 cross 64 image, which is, you call it as a primitive sketch, and then you send this as an input along with the text description again, and then you send it to another GAN, and this GAN will basically upsample the 64 cross 64 into a 256 cross 256. So to see more clearly, you can look at the figure below. So as you can see in this particular text description, we have this entire short to three lines. This bird is gray, etc., etc. So, like we always say, whenever we have text, to represent any text, we also saw in week 6 and week 7, to represent any text, we assume word embedding for that particular text. So, word embedding, like I always say, it consists of like a huge dictionary of thousands and thousands of words. Each word we give a vector representation. Like a simple way would be just give numbers to all of them, like 0, 1, 2, 3, 4, and maybe that numbers itself is like a representation. But instead of that, we give them a vector representation, like vector of so and so dimension, and each word will be given a certain vector representation. So this particular text description will then is consisting of such each word's vector description, and it's a combination of all these words, and you can form an embedding queue. So how this embedding generates, you can look into methods like word to vec or ngram model. These are NLP techniques. So that is out of the scope of this particular course, but it's obviously you can look into those techniques on your own, and we just take those techniques automatically, like word to vec or some embedding, and then we use that over here. So the text is first converted into a word embedding queue, and now this word embedding along with your noise, which is your sorry, this conditional thing which is coming, which is taking the word embedding, adding some noise from the Gaussian distribution, and then you generate this z, which is our latent variable, which we usually use in GANs. So this z now is sent to the generator, and the generator upsamples. As we saw in the last class, upsampling is done using transpose convolution, and from this vector size you go into this upsampling, and then you generate a 64 cross 64 image. And now once you have the 64 cross 64 image, you also have the real part of the image, because you have your data anyways. It's a paid data. Every text has its corresponding real image. You take that real image along with this, and then you send it to the discriminator and identify whether it's a real image or fake image. So this entire stage one generator and discriminator behaves exactly like a typical GAN will behave. You take a latent space Z, you generate an image from the generator, and then you have a corresponding ground truth image, and then you compare with the help of a discriminator whether these two images are coming from the same real distribution, or are these one is fake, one is real. So training methodology remains the same, the loss functions remain the same. The only difference is the Z which is coming is no longer from a single Gaussian distribution. It is coming, it is basically combined with another half of the vector which is coming from the embedding along with this augmentation part. So this is a standard augmentation. We assume a Gaussian distribution mu and sigma, and to add the randomness, we take this epsilon from normal distribution and add it over here. So as you can see, epsilon is multiplied with the standard deviation sigma, and it is added with the mu. So the entire training process happens for stage one this way. And once you get this 64 cross 64 image, you then take this stage one result, which is you can see on this below diagram, along with that embedding, Q embedding basically, Q and the conditional embedding which we get from here. And then this embedding along with your 64 cross 64 is sent again to a generator, and sorry, it's first downsampled to latent vector. Now this latent vector is again sent to the upsampling. So now the generator is a little bit different, and it's no longer a simple decoder, like a sorry, it's no longer a simple encoder, the generator. Here we have kind of like an encoder decoder architecture, where the encoder and decoder architecture is trying to scale, like basically highly resolute the 64 cross 64 image into a 256 cross 256 image. So in the traditional GANs, we just use a simple encoder type of a generator. Here, the generator itself is an encoder decoder architecture, and there is a residual block, which, as sir explained in the class, it's added so that the semantic information is retained. Uh, you can always look into exactly how it is added at what layers in the paper and also in the recorded lectures. So once the 64 cross 64 image is upsampled through the stage 2 generator to 256 cross 250 image, then you have your original 256 cross 256 image also, and then you basically combine these two, and then you send these two as an input to the discriminator to identify whether it's a real image or a fake image. And finally, your entire process is called as this stack GAN, and your model will be able to generate a particular image in that using the text embedding. Like using a text description, it is able to generate a particular image. So I hope this was clear. Maybe I'll quickly pause for a minute or two. If you have any questions, you can unmute or you can put in the chat. If there are no questions, then we go to another type of a GAN, So since in this particular week we talked a lot about different GANs, I'll just try to complete as much as possible about these, which usually are more popular or more important type of GANs. Obviously, you can look into the recorded lectures for more in-depth workings and all. So over here, I just try to give more examples, and obviously there'll be code walkthroughs of these particular GAN models. And also, I was thinking maybe we can talk a little bit about the assignment problem where you had to code your attention mechanism. So yeah, so for this particular week, it's mostly going to be different GANs and a little bit of code walkthroughs of those GANs. So the second type of a GAN which was discussed is called the ProGAN or progressive GAN. So again, the concept is similar to what stack GAN was. In stack GAN, basically you first generate a temporary, like a primitive sketch, right? 64 cross 64, and then generate a bigger 256 cross 256. ProGAN goes one step forward. It says, why just stop at 64 cross 64? Instead, you keep on generating different images at each level. Basically, progressive GAN, right? So progressively, you keep on generating the images like 4 cross 4 image, 8 cross 8 image, so and so, so and so. Then you come to the image size, final image size, which is 1024, and then again basically the discriminator will take this as an input along with the real image, and then it keeps on downsampling it. And at each step when you get, you keep on at so- yeah, sorry, at each step when you get, you keep on adding the particular 4 cross 4 output to the output of 8 cross 8, and that addition is acting again like kind of like a residual connection, which will help in maintaining the semantic information. So progressive GAN is basically taking stack GAN to a step ahead, where after each particular latent output, you keep on adding the outputs and make it more and more realistic as possible. So this is how the this is how the program works. And then so these are some standard modules, you can say, which was introduced in progressive GANs to make it better. The major one was this particular mini batch standard deviation module. So what this does is, so in standard like in normal batch normalization, we take the deviation of each feature in the spatial location of that particular mini batch and we average it. But sometimes what happens is the generated image from the generator, it might not generate diverse samples as the real images are there. So to balance for that, you add basically the mini batch standard deviation for each feature layer to all the other later layers in the discriminator. So in that way, you're basically maintaining, you're telling the discriminator key, okay, there are generator doesn't just generate a certain type of images, it can generate a diverse set of images. So that is why this particular type of addition is done. And then there are two other important things called equalized learning rate, which is for the training process to happen smoothly, and pixelized feature vector, so that the, again, this is also to bring the training process to be done faster, because now you're normalizing each feature vector of each pixel so that all of them lie in the same scale. So these were the other some minor improvements, you can say, which was done to the progressive GAN, which was this. So I'll again quickly pause for a minute or so. If you have any doubt about progressive GAN training process, you can just ask me. You can either unmute or you can just put it in the chat. Okay. If there are no questions, we can move forward. So then we come to simple tasks called a domain translation task. So in this task, as you can see, you have two different types of domains. The left side domain is like a sketch, like a what do you say, a very b- poorly done sketch, you can say, of a cat. And the right side is the image of an actual cat, how it looks. So is there a way possible that if my input samples are all of these poorly drawn sketches of different things, not just cats, can there be a model which can take this poorly drawn sketch as an input and generate an output of a realistic cat or realistic object? It cannot just be this type of sketch to real. It can be anything. It can be going from one domain. That domain could be weather conditions if you're talking about autonomous driving. It could be going from summer weather to rainy weather. So what we want is we want a model to learn to adapt based on all the data it has taken from summer to and adapted to the winter. That will be the output. Can there be a process? Can there be any method that can do that? So for this particular task, there were some methods, and we'll discuss a supervised method called pix to pix. There are certain other methods. In fact, if you go ahead and look into something called as unsupervised domain adaptation or domain generalization, there's an entire subfield uh, existing which tackles this particular adaptation tasks itself. It's a very interesting field. You can always look into that in depth to understand what that field is doing. But on the overview, the field is basically trying to adapt from one particular domain how you can go to another domain. So is there any method which we can do which exists, which learns the underlying distribution of that input, then changes somehow and generates an output which is from a different domain. So in pix to pix, basically we use this particular type of training methodology, you can say. So first we have a simple particular styled maps. So you can see that simple styled maps is like the input, and sorry, simple style maps are the input. Target style maps is what we want. So you can see the difference. Like target style maps has more black and white and it's more clear, whereas simple style maps is not that clear. There are a lot of boxes actually. There are a lot of bounding boxes and all like across drawn across the image. So we basically want to eliminate all those things and generate something as simple as this. So how to do that? So we assume first a encoder decoder architecture for the generator. So this generator basically consists of an encoder first, which encodes this image into some latent embedding. And this embedding, like for a typical GANs, we take from some random noise, right? We take Z to be some random noise. You can assume that the Z is this over here. So this Z is coming from the encoder embedding. Now this Z is then sent to the generator to generate a particular image which belongs to this particular style. And now, obviously, how you train your generator, we use the discriminator to say ki if the generated image uh, from the generator is how close it is to the real image. So if the discriminator is not able to distinguish, then we have completed our task. Then we can say that the generator is able to take the input from one particular domain and it is able to generate in another particular domain. So very simple again extension of GANs. All it has done is basically the Z vector is now coming from an encoder rather than coming from a normal distribution. So you can see something like this. Here they used a unit based architecture in pix to pix. So this decoder part is basically your generator over here. So the encoder is this simple unit encoder, and we use skip connections across the encoder decoder. Maybe a quick question to keep it more interactive. Like when we were discussing unit architecture, I explained why skip connections are important or needed, basically how it helped the model. Maybe if anyone knows the answer, why do we need the skip connections between the encoder and decoder in the unit architecture? You can either unmute and say, or you can put it in the chat. Any guesses? Maybe I'll just repeat the question once. Why do we need skip connections between the encoder and the decoder for a unit type of an architecture? So it's nothing related to GANs. It's more related to the unit architecture which was used in segmentation. Okay. So the reason actually is it's actually written over here also. So basically, it helps to retain low level features. So what I mean by that is, let's just say if I take this image itself, and when you look at an image, you know this is a bag. But if you closely analyze why we think it is a bag, because we say ki, okay, it has two straps at this particular side by side location. It has a hook kind of a thing in the center, and then there is a flap opening, and then there is a bigger base, and these are all different information. Like if you basically look closely, these you can say ki these are all small blocks which you combine together in a certain combination, and then you form a bag. Because if this particular strap is not at the side of second strap and it is somewhere else, it won't become a bag, it will become some other object. So this is called a spatial relation between each particular patch image patch. So this spatial relation, you are as a human understand, and you basically say ki this is a class. Now an encoder is also doing, since what encoder is doing, it is looking at the original image. So when it is encoding, it is making the size smaller of that image, but it, since it is seeing the original image, it knows the spatial relation between each of these objects, each of these image patches. But once you reach this bottleneck feature layer, which is just a simple vector, now from here, now you're when you're upsampling. Upsampling is what, going from smaller dimension to a bigger dimension. So when you go from small to big, there are a lot of dimensions which has no information. So it will be some random noise, or some noise will be there in that a lot higher dimension. So because of that, you keep on filling in different informations to, make it upsampling, but that information filling might be wrong, to in the sense that the spatial information can be lost. So to maintain that, okay, this image patch should be over here, that information you're basically translating when you're doing the skip connection. You're basically sending this information from this particular like a relation between these two straps across to the decoder using the skip connection. I hope it was clear what I mean by skip connections for the encoder decoder. If you have any questions, you can always ask. I'll move ahead for now. So yeah, and then the loss function for this particular GAN, basically this particular pix to pix GAN is this. We use a L1 loss function where this is forces the generator to generate images close to the ground truth, and also the final of the C GAN, which we always use, where the min max basically is like a normal GAN architecture. And then one another thing in Pix to Pix is what they do is when the decoder discriminator part, when they're trying to identify whether these two maps both are real, or one is real, one is fake. So they said ki instead of using a direct decoder which just takes these entire maps, decodes it down to just a two layer output, which says ki whether uh, uh, one layer output actually, which outputs one if it's the same image. If it's opposites image, then it outputs zero. So instead of doing this, uh, taking the entire image and reducing it to one point, they said ki the discriminator should be something like patch discriminator. So what I mean by this is, so they built an entire model also, something called as patch GAN discriminator. So what it does is, it looks at image patches of this particular input image. Like if I say, if I send this target cell maps, which is 256 cross 256 as an input to discriminator, then this will be the target map, which is a real image. And then this particular thing, instead of original discriminator, it basically takes this entire image, condenses to these 2 points. But now it says ki just look at this particular image patch. It's not pixel, you can just imagine as a patch, it could be more than one pixel. You basically take these image patch, you just look at this image patch and say whether this image patch is fake or real. Forget about the entire image. So in this way, you're now making the discriminator look at particular parts in the model and say if it's fake or image. So it's more robust. Now this generator has to do even better task at generating real images, because the discriminator has the ability to not just look at the entire image, but to look at parts of image and also identify whether it's a fake image or a real image. So because of this, now the maps generated were by the generator were even better, even close to real maps of the target. So this was patch discriminator. Again, maybe I'll quickly stop for a minute before I go on to another topic called mode collapse. If you have any questions, please ask. Okay. So moving on, then we talk something about mode collapse. So it's a very common problem in GANs. So the reason this particular, okay, firstly, what mode collapse means is when my generator, so we assume that the generator at the end of the day is trying to understand a distribution. That's what we said, right? Generator is learning a implicit distribution of the input data. And now input data in any real world problem, if you take that particular input data, if some for some reason, let's say assume we found out what is the true distribution of that input data, most of the times it won't be belonging to only one mode. When I say one mode, you can think like if you assume peaks, right? If you assume in a Gaussian distribution, it has standard Gaussian distribution has just one peak. So it is called as unimode distribution. Now there are certain Gaussian distributions where you have two peaks, so it's multimodal. So real world data usually has a lot of modes. It's always multimodal distributions. But when the generator is learning these real world input distributions, there can be a scenario which is possible that the generator will just fix on that particular one particular mode. It will focus only on that because maybe that initially gave good results, like it was able to fool the discriminator with that particular mode. So it just sticks on that and it keeps on generating images belonging to that particular mode. Now, what happens because of that? You won't see diverse samples being generated from GANs. GANs will only focus and on generating one particular type of image, because that particular type of image was giving good gradients, less loss, and then so it's fixed that this particular mode only it will focus. So that is called as mode collapse when there is no diverse data coming out of generator. So the same thing. So why does it happen is also why does mode collapse stick into place is because the gradient starts get for the generator becomes zero, means the loss is actually very less. So then the generator is not motivated to generate any other diverse samples, because it is saying ki, okay, at the end of the day, if you look at all these neural networks, all it wants to do is reduce the loss. So think of it from that perspective. The generator will be like, why would I want to generate diverse samples when I know ki this particular type of sample is giving me zero loss? So it's intuition is like that. But inherently, for our particular task, we want the data to be diverse. So we then come up with different types of rectifications, like we use Wasserstein GANs, we use other type of GANs where we can basically reduce this mode collapse, and we can now have the generator generate diverse samples or at the same time reduce its loss. So that is, in fact, if you look into the lectures also, there you have GANs like MUNet or UNet GANs, which does this particular thing only. How to avoid mode collapse, basically. Okay. I hope the mode collapse was clear. If you have any questions, like always, you can stop or you can post the questions in the chat. So moving ahead, then we talked about again. This is another different type of a GAN. So in this particular type of a GAN, yeah, Shravani, you can unmute and ask. Shravani, did you have a question? Okay, fine. Uh, so moving ahead, so this particular type of a GAN called IC GAN. So what IC GAN does is, it you can think of IC GAN to be useful for editing an image. Like for example, if you have an input image like this, and for some reason you want to change if you have a simple editing task, like for example, reduce the brightness, increase the brightness, you can just use directly. Like you can write a simple Python code for it and just make it fast. But if something more higher level editing is needed, like I want the hair to be black, or I want the skin color to be more like a darker skin color, or I want the eyes to be of different colors, or some high level editing. So to do such types of editing, we use this particular GAN called IC GAN. Again, the logic is very simple. You first take your original input X, you then have an encoder. You send this encoder, and the output you get, we call it Z. Now, this is the Z which will be sending to the generator. Like, like I always said, the main idea, if you look at all these types of GANs, is how this Z is coming. Where is this Z coming from? So, if you take this Z from a random distribution, normal distribution, it is your standard generative adversarial network. But if you take this Z from, like, if you look at this, if you take this Z from an encoder of this type of a domain map, then this becomes a pix to pix. Or if you take the encoder along with the text description embedding, it becomes a stack GAN basically. So most of the times it's about what this embedding, how it is coming from. That is what kind of defines what different type of a GAN you're making. So it's yeah. So all the entire game is about understanding how this Z is, what is this, what should this Z represent, and where should this Z come from. Once you understand that for your problem, it will be very easy to use GANs. Then you'll know what type. It's always adding a generator, and then you add a discriminator, which will try to get fooled with this generated image. So in this case also, you take this Z from this encoder, but now, like I said, it's not just taking the Z value, it's more like a condition, right? Now you need a condition also along with this embedding. So now it becomes a CGAN, which is a standard extension of a generative adversarial network. Now this, what is that condition? That is coming from this particular type of vector y. So we assume that there's a vector y which corresponds, each of the input will correspond to one particular feature, and then we try to change this vector. We basically have another encoder which will encode each of the value of that particular input, and we want to change it to a particular style, and then we take this y hat as an input along with z to the conditional GAN. You can use the standard conditional GAN over here, and then you can do the same adversarial training. So, so the important part over here to understand was how to take this z and y to do this particular type of image editing. So this is how the people used and developed IC GAN. Similarly, people also used SR GANs. So the SR GAN is a different type of an extension, because in this case, although the embedding is not something different, embedding is coming from a Gaussian distribution only. The difference over here was the type of loss function they used. So that actually changed the way the image resolution of the generated image is increased. So what they did was they had something called as a perceptual loss. So this perceptual loss consists of two things: content loss. The first one, LX, is actually the content loss, and then you have something called as the adversarial loss, which is this generated LGN, LGen of SR. This is particular called the adversarial loss, and this LX is actually the content loss. And as you can see, it's a weighted combination. It's a hyperparameter. You don't have to always set 10 to the power minus 3. You can always use different values and see how it actually changes and what is the effect. But overall, what we are trying to do is this content loss. If you see, let's assume you have a neural network like a VGG16. So at some layer, in intermediate layer, like fourth layer of VGG, we take that feature map as the output, and then we take the generated feature map as the output, and then we do a oh sorry, and we sorry, my bad. We take the original image which is sent to the VGG network. We take the fourth layer output, and then we send the input from the generated image. We take the fourth layer output, and we then do this particular subtraction and squaring. Maybe just a quick question. What do you think is this loss function for the first one? It's a very simple loss function. If you look at these two terms and the overall addition, what do you think is this loss function? Maybe you can forget for now what phi and what phi and g says. Let's just assume this is x and this is y. Yes, it's MSC. That is true. So this is a so content loss is actually nothing but just a pixel-wise mean square loss if you look at it. And what pixels are we taking? That pixels are coming from the intermediate layers of a VGG network. Of both the input, for once the input will be the original image, and for the another term the input will be the generated image. So all we are doing is just finding the pixel-wise mean square loss. It's as simple as that. And this adversarial loss is again standard generator loss, standard discriminator loss, which is there in any GANs. And the combination of these two losses, a weighted combination, that is our perceptual loss. So just by introducing this loss function for and some architecture modification in a general GAN, they were able to generate images which were of super resolution, very clear and very way more clear and perceptible than your actual original image. So yes, so this is SR GAN loss. In fact, I think one of your assignment question also is implementing this. So I think you had to implement matrix form. So it's a very good practice. So because most of the times in all of the neural network up till now, whatever we discussed, deep learning and all, we always had equations like these. We had equations where you write summation, summation, and then you do a simple element-wise operation. But when you're actually coding it, it doesn't work when you do the operation element wise. We always do operations in matrix. That is why the PyTorch and all these things work faster, because they always write in matrices. So I think one of your questions is also how to convert this particular content loss into a matrix representation. So if you think about it, if you use a little bit of pen and paper, then you can clearly see how you can convert the entire operations into a matrix representation. So yeah, and so for this particular session, I think these are all the things I have planned. And if you have any questions, we can discuss about any type of GANs. Else, we can go to the code walkthroughs. So any questions on SR GAN loss or IC GAN loss or mode collapse or anything? Maybe I'll just pause for a quick minute or two. If you have any questions, you can ask me. Otherwise, we can go ahead for the code walkthrough. Okay. Let me just open the code. Yeah. So I first wanted to discuss a simple GAN, which was progressive GAN. Like there's no time to discuss all the architectures, so I thought ki maybe I'll just pick one, which is progressive GAN, and explain. And after the progressive GAN, you all you need to see is how basically if you understood the from the last week lecture only how GANs are created, right? Last week we talked about how you can create a GAN architecture entirely and do the training in PyTorch. So same things. It's just that what all modules we talked about, those are the only few things. So each model has its own contribution, obviously, their own novelty. That will be just a small block or a module mostly. So apart from that, everything else is like the same GAN template which we used. You will have a generator block, you'll have a discriminator block, and then you'll have a generator final GAN block in which comprises of the generator and the discriminator block, and then you do the min-max training. So in this case, I'll just talk about progressive GAN, and then we can go to the one of the assignment questions of the last week. So as usual, so these are the building blocks. Equalized learning rate was one of the thing which they used. Pixel normalization, and the other one was the batch. I think it was called the batch normalization, by when they're doing the addition. So these three things are mostly what was helpful in making the progressive GAN work also. Sorry. So as you can see, you first create equalized running rate from the program paper. You create this function. So like always, it follows the same template, whatever module you're creating, right? You first import your nn.module, which is your PyTorch module. You then create what this particular block should do. So the operation what we want to do is you take a pixel, you multiply the weight into the 1 by normal form, which is again basically inherently what we're trying to do over here. Pixel into the 1 by norm and into the weight. So that's what we want to be done in this pixel norm. And yeah, as you can see, this particular pixel norm basically takes that particular pixel x, we normalize it by using the square root and torch of mean and this, plus this weight, which is the epsilon part. So now we generate a final convolution block. Now this convolution block will be used for each particular convolution layer in the both generator and discriminator. So here the difference was we couldn't use a standard convolution 2D. Why? Because we wanted to add these two things. We wanted to add the pixel norm and we wanted to add this learning rate, equalized learning rate. That's why we couldn't use a standard conv 2D, but instead we generate our own conv 2D called the WS conv 2D. And now this con block will call this two things, WS con 2D and the pixel norm, and we create our own convolution block. Now this convolution block we can directly call in our generator and discriminator. So maybe you can just go through it once, how exactly the operation is happening once you get the code block. But all we are trying to do is we are trying to create our own conv block over here. That's what. Up till now we always used nn.conv2d directly from PyTorch, but now we wanted to create of our own, and this we'll use in the discriminator and generator. So as you can see, in the generator we create using the one type of layer creation, right? Which I always say, which is called the nn.sequential. So other type is you create each layer on your own, and then you basically call it in the forward function. So you have this forward function over here for this particular generator. You basically have the layers over here, nn.sequential. You have all the layers, and this initial layer, which actually will be called over here in the forward path. First, we send it to that initial x output, and then we upscale it. That was the progressive GAN. Basically, after each particular upscale, we add it and send it, we output it and we send it to the discriminator. So that is what this step is also trying to do. We find out the output after each particular upscale, 4 cross 4, 8 cross 4, and we send it to the discriminator, which I'll discuss in the next block. So this particular discriminator, again, we define the same for loop. Basically, we tell the discriminator that you have to expect different scales coming from the generator, and basically like 4 by 4, 8 cross 8, or 1024, and you take that particular input, and then you check whether it's a real or fake. So the same loop as you wrote for the generator, you use the same loop for the discriminator. And yeah, and test function, you can just ignore it for now. This is just a simple test function, like a standard test function. How do you test between the two images? Yeah. So these are the basic steps. Once you create your discriminator and generator, you can use the training loop from your previous last week's GAN template, and then you can easily see that the training of the entire progressive GAN happening. I went a little bit fast, but you can always, we wrote everything clearly, step by step, what each of these things mean. So you can always look into the code block once and you can understand. So all you have to remember is we created a new type of a convolution block which encompasses the equalized learning rate and the pixel norm. And now this convolution block is being called after each particular scale, and the generator will send output after each particular scale. The discriminator will accept output after each particular scale, and the training will happen once standard training will happen as you use for the GAN template, which we did discuss in last class. So yeah, maybe if you have any questions, you can ask, but you can always go through this once on your own. I would suggest that, and then you can ask me in the next class also. In the meantime, I'll want to discuss one of the assignment questions, I think, where you had to create your own transformers or attention. Maybe I'll just quickly go through what the attention or transformer means also, and then we can then talk about this. I think this particular assignment date has the deadline is done, right? Maybe if someone can confirm the week 9 and week 10, the assignment deadline for that. Yeah, thank you. So, yeah, this is what we want to do basically in attention. Maybe I'll just open another slide. Just a second, let me open the slide from week 9. Yeah. So just a quick recap about what the self-attention and what the transformers do, which is a extension to self-attention, which is multi-age attention, and then we can look into the code. So to recap, we had an input embedding. This embedding, let's assume, coming from word-to-vec embedding, and then we have a weight matrix correspond, and we have three things basically: query, queue, query, key, and value. How do you get query key and value from the way input embedding? Is basically you have three corresponding matrices, which is called WQ, WK, and WV. You multiply that with your input embedding, and this should be done for each word. Like for example, thinking will have its corresponding WQ, WK, WV. Machines will have its corresponding WQ, WK, WV. And then once you get your query key and value, then you do this particular operation, which is softmax of query into k transpose, which is basically the dot product, and then you multiply it with the value matrix, and the final output, whatever you get from this particular operation, we call it the z vector. Now each word will have its corresponding z vector. Like thinking will have z1, machines will have z. Now if you take the multi-head attention, so it extends this idea of self-attention with multiple heads, like the name suggests. In particular, we use 8 heads. So this thinking machines, like each of these words which was there, right? Like thinking is the first vector, machines is the second vector. Each one will get multiplied with one head. Like for example, this x will get multiplied with this w0 qkv. It also gets multiplied with this w1 qkv, so in total w7 qkv. And then each of these multiplication will result in their corresponding qkv matrices. There are like 8 q's, 8 k's, and 8 v matrices. You then do the softmax, which is this operation, this particular softmax into the dot product into v, and you basically divide with the value also dk. Once you do that, you get z matrices. There are 8 such z matrices. You then combine all of them 8 z matrices into one huge matrix called capital G, and then you multiply with another vector, which is another matrix called wo, and the final output which you get is this z. Now this will be sent to the next layer, and that you can call this z to be r basically. So this output will become the input r for the next layer, and the same process is repeated. So you have multiple layers, and each of that layer consists of a multi-layer attention. So there are some other layers also in between. So like after the first multi-layer attention, after one multi-layer attention layer, you do some addition from the previous input and some normalization. This is called layer normalization. This is operation is looking like this. You take x, you z which you get, you add it with x, and you do layer normalization, and then you send it to a feed forward to reduce the dimensions. And after this particular block, you send it to another block. So if you look, yeah, so this is how it happens. So overall architecture is this: you have your encoder architecture, which is multi-layer attention, then there is a feed forward, and then this goes to the decoder architecture. Only differences in decoder architecture, the first layers will use a masked multi-retention because it shouldn't see future values. So that's why we use mask multi-retention and keeps on going. So we now will discuss how the self-attention works, how the self, sorry, this particular operation, sorry, this particular operation works, and then how multi-retention also works. I hope this was clear. Maybe any questions in this? I'll just pause for a minute. I think this is anyways we discussed previously, but if you have any questions, you can ask me again. Okay, sure. So again, basically, we also have some notes also. You can always look into the notes. Yeah. So one use case, like you all already know, just for completeness sake, I'll repeat. One use case for encoder decoder, especially for this self attention mechanism, is for these transformers is machine translation, where you take input from a language like French, I guess, and output will be in another language, English. This encoders decoders is what consists of all your transformers. So this is how it consists. Each encoder, that main block, consists of sub blocks called encoders. You see so many encoder layers, and final encoder layer will be sent to all the decoder layers. Any To just keep it interactive, why should we send it to all the decoder layers? Why can't we just send it to one first decoder layer? It'll be done, right? Like sorry, why can't we just send it to the first layer here, Because this decoder layer anyways keeps on connecting to all the other decoder layers. Why do we have to send it to all? Any guesses? Okay. Maybe I'll explain. So you can think of it as like looking at all the possible values. So for example, you can see that when if I just send it to the first layer of the decoder, so this decoder only will see where this encoder, all the encoded values are coming. The next decoder will not know what the encoded values are. It will just see what the output of the previous decoder layer is. But sometimes, like for example, we say I am a, right after a, which is at somewhere over here. When I'm getting student, I need to see at what particular value in the encoder is there. At this position, student is there. So to see that encoded value, just looking at the previous words is not enough. I have to also look at the encoder from in the encoded values where is a and what came after a. So in a very simple intuitive way you can understand it this way: by sending the encoder value to all the decoders, we are now helping each decoder layer to not just look at the previous layer's output, but also to look at how the value input itself is encoded. So it will get a more correct how what word to predict in that particular time step. So this is why we send this encoder output to all the decoder layers. Yeah. So this is your entire full-fledged, again the same image which I just showed. So you have each block. This combined is one encoder block. You have I think six total. I think it's upon you. You can define this n. In this case, I think it is six. So you'll have six such blocks. Inside that each block, you have two like what is modules. One is your multi-retention, which we just discussed, and one is the feed forward. Uh, okay, I think I didn't explain feed forward, but right now, but maybe anyone can venture a guess. Why should we use feed forward over here? Why are we using feed forward? I think we've discussed it once in week 9 when you were explaining. But anyone remembers or anyone can take a guess why should we use a feed forward? Because anyways we're encoding using monthly retention. We can just send this output to the input, right? Why again we use feed forward? Okay. So the reasoning was what multi-head here the output will be sometimes, because if you look at it, there's a lot of operations happening. There's a lot of matrix multiplication happening in each of this self attention in itself, and then each of the self attention will have multiple heads, which causes multi-head attention. So what is matrix multiplication? In a simple way, if you think about matrix multiplication, it is nothing but projections at the end of the day. That is what a matrix multiplication is. So when you're doing these projections, right, you in these cases at least most of the time the projections are getting projected in some bigger dimensions. So from smaller dimensions you're multiplying and going into a bigger dimension. But we know ki we also know that it's not always big dimensions are needed. So most of the information always lies in some smaller dimension. So to maintain to remove some redundant information or to remove the cost of doing the attention mechanism itself, this feed forward network basically projects from this bigger dimension space, which is the output of the multi-head attention. The feed forward projects it into a smaller dimension. You can't project into very small. I think there was a ratio which I don't remember. If you read the paper, you only see there's a particular ratio to which they reduce it and project it into a lower dimension. So once you do that, it's kind of like maintaining a stable training methodology. It can be understood in that way also, instead of just keeping on, because then in that case after each layer, because using n times, right, after each layer the dimensions keep on increasing, and after a point it doesn't make sense to get any information from such big dimensional space. So to maintain balance we use this particular. I hope that was clear. So as always, we use these libraries. Again, I won't be going in depth till now. By now, I think everyone is clear about what each library does. We use the torch for the PyTorch libraries, declaring of the neural network, training of neural network. Then we use pandas, numpys for data handling, like for either data operations, matrix operations, or like visualizations of data, which can be done in Seaborn, Matplotlib, and Seaborn does that. So these are all the important libraries which you have to always import. So, like I always said, creating of word embeddings is an important step. Like we never really discuss how to do that, but because it's beyond the scope of this. But if you're interested, like I always said, you can always look into ngram models or word to vec models. That is what this embedding is basically doing. It's a very simple embedding. You can always look into how exactly the logic behind this embedding is done. I think, but in this case, we import actually the nn.embedding. So there is a standard embedding vector in PyTorch. I forgot the name of that embedding, but you can just look what nn.embedding is doing. So it's a standard embedding process which is directly imported from PyTorch, and you basically say ki what is your entire vocabulary size and what should be your embedding dimension. That basically that's vector of each particular uh, word what you want it to be, vector size. So that's what you have to give inputs and it will give an embedding done. So you don't have to worry about that embedding. You can look into what it is on your own time. And then we talked about positional encoding. So this is important. So what exactly is the position of each word in the sentence? That is very important. So that is where we use the positional encoding. And usually, I think in the paper also they use these two positional encodings, like a sine of cos by 1000 so and so formula, and another is cos. So it basically intuitively, if you want to see, I think we have over here. No, okay. I don't think we have an example. Maybe I'll try to get an example more into it. But what in you can just imagine right now, we have a sentence, right? Like we have, I am a student. The positional dependence of each word makes a lot of sense over here. Like when you're translating, right? When you're going from English to French, we need to make sure that the articles, like in English, you have different articles like prepositions and verb and all. Those all make sense if they're in a particular order. The same order should come out in the decoder time also, and each word has its own particular type of ordering in a sentence. And how is that done? That is done using this positional encoding. So you don't have to worry if you're not able to understand, because most of the times it's a given positional encoding. People use a standard positional encodings. But if you want to go in depth, you can always look into this particular code block. But for now, you can just assume it to be a pre-processing step. It's like a matrix. It consists of different positional elements for each particular word. You just add it with the input sequence. You can just assume it to be that. It's just a matrix which is getting added to the input sequence. Intuitively, it's basically trying to make sure that the ordering of words in that particular sentence is correct. So yeah, you can see how to generate this particular sine and cos. That is what this particular function is doing. This particular class is doing. Sorry, this positional embedding class. It will just try to replicate that formula, which is the sine of pos into this particular 10,000 to the power of so and cos of pos divided by 10,000 into so and so. So for now, you can just assume it to be like a pre-processing block. We'll focus mostly on the main code. Yeah. So it's also written, every step is written, what it is done. You can always clearly go back to this particular collab notebook file, and you can see what is happening in each step. But let's just walk through step by step. Yeah. So the first step, like we always, when we're discussing self attention also, is that we create a query, key, and value vector. So how to create query, key, and value vector? We take the input x and we multiply it with a wq, wk, wv matrix, and we get this query, key, and value. So each of this vector in our particular case is of the dimension 64. Like 1 cross 64 is that horizontal vector basically. It's a okay. Maybe to be technical, if anyone can tell me what is this vector called 1 cross 64? Is it a row vector or a column vector? It's a simple linear algebra question. Anyone can guess if it's a row vector or a column vector, 1 cross 64? This is a row vector because it's called a row vector because the first dimension is 1. If it's a column vector, it will be 64 cross 1. Uh, yeah. So if you look into this diagram, this particular row which you're looking, right, be it for q, k, or v, this row, one row is of the size 1 cross 64. Similarly, you will have different, for how many words you have, you'll have that many rows, and each row will be having 64 length. That is what this 1 cross 64 represents. uh, I hope I'm audible, right? Can someone confirm if I'm audible? Okay, thank you. So yeah, that is what the step one does, basically multiplying with the weight matrices, and you get your QKV. Sorry, that is the second step. Basically, after your second step is calculate, we multiply query matrix with K matrix is the second step. First step, you get your QKV matrices, and second step, you basically do the Q into K transpose, which is nothing but your dot product. Uh, and okay, maybe I'll just keep it simple, and just this is just to make it more interactive. So what do you think dot product does? Why do we need to multiply q and k transpose? Any idea why the dot product over here? Okay. So here we are doing the dot product, like the word concept over here is like attention, right? So attention is basically similarity. So how similar is my two matrices? That is why basically what we're trying to do over here is we're trying to see how is my input depending on my input itself. What I mean by that is, if you look at this particular example, I am a student. Let's just assume this is the input value. When I do a similarity on my own vector, what I'm trying to do is I'm identifying how close should I and am be, how to I and a and I and student. So we are trying to find out in this sentence the closeness of each word. This is looking only at the input, this particular input, this French sentence. We're looking at how similar or how close is each of this word with itself, with the other words in that particular input sentence. We're not looking at the output, right? That's why we do q cross k, just to look at its own attention. That's why the name self attention, basically, where you're looking at your own self, right? That's why the name self attention. So yeah, we calculate in the second step we calculate q into k transpose, and then in the third step I said, like, we have to divide it by a square root of the dimension of k matrix, which is I think in this case, where 8 is the dimension, and then we apply a softmax over it, and then in the fourth step we multiply it with the value matrix which was generated after the first step. And once we have all these done, we send it to the linear layer to get to a fixed output. As I think the output, uh, yeah, the final output what we get after passing it through the linear layer is just 32 cross 10 cross 5. So now this is self attention. Now we repeat this n number of times. Sorry, 8 heads. So it becomes a multi-head attention. So that's what we write in this particular class. So we call class multi-head attention, which is basically the again importing your module class. Then we look at your embedding dimensions, and then number of heads we want. Like I said, in this case we want 8 heads, and then we have our query key and value matrix. So okay, a simple question again. Why are we using linear nn dot linear over here for query key and value matrix? I think you should guess this one. Like, why this nn dot linear? How are we generating query k and value matrices with this nn dot linear? Yes, correct. Like Abhishek pointed it out, fully connected. So at the end of the day, nn dot linear is nothing but matrix multiplication, right? So that is what is basically we're trying to do also here. And each of this will have its we have to specify what should be the input and output dimensions, which is in this case 64 cross 64. So once we define, after all these initial definitions of what each of these particular layers should do, we then define a forward function which will now send the data through all these layers. So if you look, so we get the input. Sorry. Yeah, okay. So here we, sorry for the delay. So here we first find out the key query and value, value matrix. This is basically your QKV matrix, which is basically the multiplication of the input. You can see over here. This is a batch size, the sequence length, number of heads you have, because now we don't do it like we did it over there, right? Where we did it for each particular head and then we add it. Instead, we are trying to do directly for all the heads. So we are combining the number of heads also. So it's a little bit of matrix manipulation is needed. Maybe if you look into the code, how it's actually done by making all the heads combined in one particular operation, you can quickly figure it out. So once you get the k query and value, you send it to your you get your k, q, and v values, and then we do the formula, basically the k transpose we calculate, then we do the q into k transpose, and then we have to do the softmax, which is this. Sorry, first we divide by the square root, the product which is coming after the q into k transpose. We get your divided by the root of d, and then we do the softmax, and then we multiply that softmax, which is the scores, into the v matrix, and then I think we concatenate all the values, and then we send it to a final linear layer, which is your which is defined as self dot out, and you get your final out. So this entire thing is basically defining one particular multi-head attention block, so which is this particular layer. So we finished with the multi-head attention and the feed forward network. So you can call it at one encoder layer we completed. We name that as multi-attention because we assume that feed forward is inherently inside it because nothing new is happening. So this particular block is what we define. Then we repeat this multiple times. How we do that? You look If you look into the code below next. Now we have a transformer block, and here we define the self attention, which is self attention, which is our basic multi-head attention. We create a class called self attention. If you look, self attention is coming from multi-head attention, and then you have your encoder. Sorry, yeah, this is a transformer block. Yep. And then you here have your module list. How many blocks do you need? That's many blocks you want. You have number of layers. So if you define a number of layers, that many particular transformer blocks are being formed in this module list. And then a forward function, it simply takes that X and sends to this layers after positional encoding and all. It will just send it to this particular layer. So as you can see, this for loop, what it indicates is, now if I create a list of 4 layers, now this I'm calling each layer, calculating, sending an input, getting an output, and that output will become the input again for the next layer. So that's what this for loop is doing. So instead of writing n times the same transformer block, we basically create a module list which will inherit how many ever transformer blocks we want, depending on the number of leaves. And then in the forward function, we write a simple for loop where we take the output of one particular layer and send it as an input to the next layer. So there's not much happening. If you look at it again clearly, you'll understand. So, and similarly, we have a decoder block. So in decoder, we have a output embeddings, a positional encoding, and then we have a masked multi-attention. We have a normal multi-attention. This consists of one particular decoder block. We repeat it n times, and we finally finish our entire decoder network. So maybe I'll just pause for like 1 minute. If encoder is clear, we can move ahead with the decoder. Any questions or any doubts? Then, like I explained, we'll again look into different steps in the decoder. So we first get the outputs passed through the embeddings, and then we have the positional embeddings for each of this particular input embedding, positional encoding for each of this input embedding, and finally you get each particular output word or embedding has a size of 1 cross 512 vector. And then in the step 2 we pass it through the multi-layer attention layers like we created before, and then we get an output vector. And yeah, how is mask working is mentioned over here. So like I said, why do we need mask? We need mask so that we don't look into future values which still didn't even come into the picture when we are encoding, right? So when you're looking at the sentences in the decoder, you have to look at only the decoding state words in that sentence that has been decoded up till now. What I mean by that is, if you look into the example, look at I am a student. So each of the decoder will output each of these words. Now, if I am at stage am, so the second decoder has outputted am. The second decoder should not look at the all the other future statements, words that are possible, which is a and student. So here we are using mask to basically blind this, and we have to look only at this. So it's a simple, so whenever any masking type of a job comes in your coding, right, always go for the Boolean type of a logic where in that particular matrix you create ones for all the ones you want to see, you create zeros for which you don't want to see, and then you use a simple operation like dot equal to or dot equalize or something. I'll show you what, and then you can easily identify how the masking is done. So similar thing, if you look over here. Yeah. So we create simple ones and zeros for ones which, if you look at the first one, right? In the first one, we want only the first one to be one because we are seeing only at that. In the second word, we saw these two words, so two of them are one and remaining are zero. And then similarly, we create an entire matrix like this. This is usually called a triangular matrix. I think this is upper triangular matrix. But what I meant to say is we create a triangular matrix where all the elements above the diagonal are zero. So now we can quickly use a Boolean operation to identify all the spaces for one. So you'll know what is the mask that is being formed. And then you finally add a norm layer basically, which we added in the previous layer also. And then this you add and normalize the layer like we did. Like we did for the encoder layer also. And next again we send it to the feed forward linear layer, which is very similar to what we did in the encoder. And finally, we create a linear layer with equal length to the total number of words in the target output and a softmax function so that we'll identify which word is being predicted, what is the probability of each word. So again, we have the decoder block, attention, multi-attention. You can quickly see we import the same. Even forward function for the decoder block remains the same. You just take the input and send it to the self attention, and you have a little bit of transformer block over here. You can just look at it's I'm going a little bit fast because it's the same logic which we used previously. You can look into the code. And then we have the transformer decoder. So here this is the final decoder block where you take the x, send it into the word embeddings. This x is coming from the encoder basically, and then you do the positional embedding of this particular x, and then we send the same logic which we use like number of layers where we send each of this output of the previous decoder layer as the input to the next decoder layer. And finally, we use a softmax. The softmax is used only in the decoder layer to finally identify over the probability over all the words that are possible in the target. And then we create an entire block of transformer which consists of both the encoder and decoder. So we create transformer, and here is the forward function where you take your source, send it to the encoder, and then you take your target, which is the encoder out, and you send it into the decoder. And in the meantime, you have something called as mask, target mask, which we created using the ones and zeros, and you send that into the decoder, and finally you get the output, which is the softmax distribution. A simple test, you can just see what the model looks like and everything. Yeah, so this is more or less the transformer code. I hope this was clear. So this is what I planned for this particular session. If you have any questions related to this or any other topic which we talked in the beginning about GANs and everything, I'll be happy to answer it. Otherwise, you can leave the session. That's what I had planned for this week. Thank you all for joining. Yeah, sure. Yeah, I have shared it on the chat. Okay. Related to what, if I may ask? If Tyagaraja, if you wanted the reply on discussion forum related to what question? Is it an assignment question or fine? I'll message the TA person to reply to it. Jitendra, were you able to mail the NPTEL people, NPTEL support staff or something? Did they reply anyway or didn't reply? Okay. Yeah, I'm also not sure because usually that's the only source where you can mail and ask them because they only handle it. I'm also not sure. Then. Maybe I'll just convey the same to the professor and the other TAs also. Maybe they'll be careful for the next time. If there are no further questions, I think we can. Yeah, Jitendra, you have a question. If there are no further questions, I think we can close the session. Thank you again for joining.